Well, you might not believe me, but it turns out that something moving in a straight line is technically spinning. We gotta figure out how this works. So we have this thing called angular momentum. And there's a bunch of different ways that we can define this as usual. So let's go ahead and just mark those down. Maybe we're just given distance times velocity right here. Maybe we're given r, p, this is momentum, r cross p, and that's going to be the same thing as iw, and it's also going to be rmv sine theta. That's just rewriting this, and then we have L equals m, or rmw, or gosh, mwr squared. Great. So these are the 4 or 5 equations that we have to calculate angular momentum. It's always going to be kgm squared over s. Those are the units. And we also have a little example that goes along with this. Let's say we have a plank of wood here, and there's a box. And we also have a bullet over here. So we're moving pretty fast with some sort of velocity, some kind of momentum towards this box. At some point, it's going to get embedded. And before it embeds itself, just before the moment of impact, we're going to want to calculate the momentum. What kind of momentum? Not the linear momentum. That's not really going to help, because we're going to try to figure out, afterwards, once this thing starts spinning along this axis right here. In fact, that's really important. We're going to mark this in red. The axis. This is the axis right here. That's necessary. For something to have angular momentum, you need that axis. That's why we have the theta. All right. So once this bullet is really, really close to that block, it's going to be basically 90 degrees, the sign. So that's going to go away. And we're going to calculate the initial momentum. And we're going to want to set that equal to the final momentum. But the initial momentum, LO, is equal to RMV. That's because sine of theta is going to go away. Now, once this thing hits that, the final momentum, LF, is going to be essentially the same thing. Remember that here we're combining these two masses, RM plus MVF. And we're going to put this as initial velocity, final velocity. And this is what happens when two things collide. All of a sudden now, the combined masses, you're still going to have the momentum. Conservation of momentum is going to stick around. So that's gonna work out. Now we can calculate how far perhaps this thing would spin, because you're gonna have some sort of kinetic energy, and then you want to know how high does this move. Here's the floor, and here's the height. You want to try to calculate how high this would go if you want to try to figure out what potential energy is. So let's try to do some calculations here. It's a little bit of geometry. We're just going to do the parallel line here and here. Okay, this is going to be, usually this would be R. The full length would be the radius, right? But we're going to be cutting off some of it right here. We're going to be cutting off H, R minus H. And then over here, we have another R. This is the entire radius. And here's our angle theta. And we want to try to figure out how high does this thing move after it gets hit. Well, let's try to figure out what H is. H is going to be, if we take cosine of theta and set that equal to adjacent side, which is this from here to there, over the hypotenuse, which is the R, R minus H over R. We can rewrite this, take the R away from that side, put it on the other side, and now we're going to say that H is actually equal to R minus R cosine theta. And so we can get a final answer of H is equal to R, and then 1 minus cosine theta. And so there we go. That's just a quick shortcut to figure out what H is. That's if you're trying to calculate potential energy and how high that would go. It's pretty important to know that. Let's take a look at torque. Well, turns out that torque is really similar to force. Force is mass times acceleration. Torque is simply inertia times angular acceleration. It's kind of interesting. It's in Newton meters. And we can say that T, here's a little strange looking T right there, and it's going to be equal to R cross F. That's just RF sine theta, similar to what we'd had over here, but usually things would cancel out and you would get RF, kind of. We're going to try to set that up. You'll see how that works. Here we have a T that's going to be equal to I, and then here's alpha. This is inertia times angular acceleration, okay? And over here, one final equation that's really critical. This is going to be one way to solve a whole bunch of different problems, is that RF equals IA, okay? If you're given just the radius and the force and the inertia, and you're trying to calculate A, that's nice. There you go, you've got 4 different equations all in one, well, 4 different variables in one equation, so that's really nice. And let's take a look at how we want to set up torque, because let's say what you really want is both of your forces to be at 90-degree angles. You want all of these forces, whatever forces, you want them to be at 90 degrees, because if they're at 90 degrees, then sine of theta disappears. So you want the torques to be like this. This one's going to be going the positive direction when it's counterclockwise, and negative when it's going clockwise. And of course, it's normal that as the radius increases, the torque increases. That makes sense, because if here's your axis, if you're trying to push on this, it would be a lot easier to push it here, and it would be a lot harder to push it around here. So the further out you go with the same force, you're going to get a bigger strength. Obviously, if you get the same force and you increase R, you're going to get a bigger torque. That's how the math works. Now, how do we set this up if, for example, you get a force that's like that and it's not really 90 degrees? Well, then at that point, you're going to need to try to set it up so that you can get what the component is here. So you're probably going to be given this theta, and then you're going to have to do some geometry like we did over there. So this is the force they gave you, right? Let's say they give you this force, and you want to try to figure out what this x is right here. So you're going to say that what is this, the opposite? So sine theta is going to be equal to x over f, and then put the f on that side, and now you're going to get the component. So this is going to set you up. Now all you have to do is figure out what the r is from here. What's the r from there, here to there, and that's your r. So then the total would be technically RF sine theta, and that's exactly what you would get, RF sine theta, if that's your R, okay? So you can see how, like, if you just try to figure out how do you get this to be 90 degrees, it's essentially already plugging it into your equation, but sometimes it's actually cosine. So you do want to work this out and try to make sure that you get this to just be 90 degrees properly. That's the example for torque. It turns out that angular momentum and torque are actually related. If we were to take the derivative of angular momentum, we could do this instantaneously, or the average, that is equal to torque. All right, and then we can also say that the change of L equals total torque times change in time. So angular momentum equals torque times time. And then we can say that work is equal to the integral for theta of torque d theta. And this is a really important equation right here. Work is equal to the integral of torque over d theta. All right, so now we're ready for our example here, our final example of torque, essentially. And there's a point where something might be completely still. It's called equilibrium, static equilibrium. For this example, let's go ahead and set this up. We have some kind of a cable here, and it's attached to this plank. And we're going to try to figure out what are all the forces that are going to keep this in static equilibrium. This is kind of what we got to focus on here. Static equilibrium. And what that really means is that all the forces equals 0. That's going to be the forces in the x directions and the y direction. So Fy equals 0, Fx equals 0, and it turns out that the sum of the torques equals 0. So we have to do 3 different sort of calculations on this, and we're going to start by drawing our force diagram. I already drew the first one here. This is the tension force from the cable right here. Then we might have this this plank of wood right here that's kind of resting along there, and we're going to have possibly like a friction force right here that's pulling up, preventing this from slipping down, and we might even have the normal force that's pushing back over here. Right on. So we can figure out what the Fy is by sort of starting to plug in some numbers. Fy is going to be equal to the positive side here is going to be tension, it's T, and I guess it would be tension like this though. We have to calculate like this. This is our T, that's our theta, and this is going to be our y. So sine theta equals y over t. Move the t over there, and we'll get y. So that's really just going to be t sine theta. T sine theta. And then we have minus mg. This is just going to be the weight of the plank right over there. Okay? And it turns out that this is all equal to 0. That's a minus sign, not an equals, by the way. This equals 0. So you can set these two equal to each other. T sine theta is equal to mg. And if there were more weights on here, it would just all be equal to whatever weight is on that side. That's because this is in static equilibrium. That means that nothing is moving. Okay? It's completely still. Now we're going to figure out what the fx's are over here. Fx, that's going to be on the right side, this is the normal force, so you can say N. And then on the left side, that would be this. It would be the opposite of that tension, so it would be minus T cosine theta. And naturally, you can set these to be equal to each other because turns out that this is all equal to 0 over here, right? So that's going to be equal to T cosine theta. Nice. And you've got these two nice little neat equations that you can refer back to. Cool. And then finally, we can focus on the torques. So that's going to be torques. The torque is going to be on this side is going to be positive torque, right? What is the best torque? Well, first we have to set our axis. The cool thing about static equilibrium is you can choose the best axis, choose the axis that has the most amount of forces with the most forces. So we're going to choose that axis right there because that's where the most forces intersect. And so now we're going to use the perpendicular, and this is 90 degrees right here. We already did that calculation before. It's just going to be T sine theta. That's going to be the positive torque, and the minus torque would actually just come from this mg over here. But this is going to be r over 2 because this length right here would be length of r, and that's divided by 2. Let's not forget the r over here. This is coming straight from the end, so this is r. Oopsies, RT sine theta, and then this is going to be minus R over 2, and then mg. We don't need any sign there because it's automatically 90 degrees. So we've sort of figured out what the torque is on this side. This is equal to 0, which, well, hey, that means that you can say RT sine theta is equal to r over 2 mg. Turns out the r's are going to cancel, and you're left with T sine theta is equal to 1/2 mg. And that's kind of a cool little equation. So yeah, these are just basically, the static equilibrium is really easy. That's why I even just included it in here, because you can see how it's basically, you're going to have to deal with torque a lot. And so it's just kind of a practical example of how you can use torque. And simple, cool. Now, hopefully, now that you've started to realize how angular momentum works and torque works, how all this stuff ties back to each other and how it's all combining together, this is really cool. It turns out that the whole point of physics is whether something is spinning or not, or if it's moving or not. That's why we even included static equilibrium here at the end. So the next concepts are going to be really complicated. We just got simple harmonic coming up next. And that's going to be so many different equations. So hopefully it's not going to be overwhelming. Now, if you enjoy this stuff, make sure to like and subscribe and ask any questions you have in the comments. Thanks for watching.